In the last lecture, we talked about, how the atomizers, well, they are essential, to cause the atomization of the sample in atomic spectroscopy. They also cause, this problem, referred to as the background. Now, you're gonna find in an ideal setting, ideally your signal, as a function of time, should look, like that. Now, meaning that when there is no, analyte, or when there is the blank, you essentially, have a signal being equals to zero. However, we know that's not really the case, because in real life, typically you've got a situation, that looks like that. Meaning, even when you're running the blank, there is still a little bit, of signal that is related to the blank. And this signal of the blank often is largely, because of these kinds of effects, from the laser, if at all is a light source, from the flame, if at all you're dealing with the AAS, for example, or flame AA, or even, something like the plasma, if at all you're dealing with ICP. So, of course, you would see that situation like this really affect your signal to noise ratio, which obviously, affects your limit of detection. Your limit of detection gets affected, because of that situation. So as an instrument, manufacturer, you really need a way to correct for background correction, in your instrument. Now, we're gonna discuss, different ways of doing background correction when you're doing atomic spectroscopy. And one very common way of correcting for background related to the flame, for example, is by simply modulating, your light source. So if at all you've got your light source there, of course, remember that is a hollow cathode lamp. In the case of AAS, is the most common. You can modulate the lamp such that you are pulsating it, meaning you're switching it on and off. And in that case, when it is on, then you're really detecting both the matrix or the background, as well as the signal. And while it's off, you're only really detecting the background. And when you subtract the two, then you're only gonna get your signal. Another approach, of modulating is where you just simply have a chopper. It's still a method of modulating, really, where you've got a chopper, a beam chopper, that is able to block, the light, from the flame. Meaning at one point, you block the lamp, from getting to the flame. And so in that case, the detector here is going to only be detecting, the signal from the flame. Okay? So when the lamp is off or is blocked, the detector is only detecting, the signal from the flame. When the lamp is on or is not blocked, you're detecting the signal from the flame, as well as, the signal, from the light source, from the hollow cathode lamp, and essentially this is the analyte signal. Okay? And of course, this one is a matrix, signal. And so if you subtract this, from this, then you're only gonna get your analyte signal. I hope you've seen how it works. When you blocks, the light source, you're only detecting the analyte as well as the matrix or the background. And when the light source is on, you're detecting both. And as such, if you subtract the two, you're only gonna get the analyte signal. Another method, of doing background correction is where you've got two light sources, okay? So you've got the hollow cathode lamp, which is sort of your analytical, light source, but you also have, a continuum type of light source, something like deuterium. Now remember, this one, the holocathode lamp, is a line source. Whereas, the deuterium, is continuum, meaning, of course, the wavelength is fairly broad, so this one is a continuum, is a continuum light source. And so at one point, you can have a rotating chopper here, that blocks the light, from the deuterium, meaning your atomizer here, where your sample is, it's only being perturbed or impinged really by the line source, and in that case, you are detecting, the signal, from the analyte, plus, also the signal, from the matrix. Okay. Now, when you rotate the beam chopper, on the other hand, such that the deuterium now is the one that is passing through the atomizer. In that case, because it's a continuum, you're going to be detecting largely, the matrix effects. Because remember, the analyte is only responsive in a very, very narrow wavelength range, meaning it's only going to be almost negligible if at all you've got a continuum light source. So with a continuum light source, when it is on, you'll be detecting really, the matrix rather than, the analyte. And so if you subtract the two, then you're actually gonna get your analyte signal. And as such, it's a way to correct, for the background. So this is very, very common. You're gonna find actually lots of different instrumentation use also this type of background correction, where you got two light sources. One of it, is a holocathode lamp, and the other one, is a continuum, that's largely gonna detect, the background that is coming from the matrices in the atomizer. And another method of doing background correction, is what they call the Zeeman effect. And I think I mentioned about it, previously when we were talking about band broadening. Now, the way the Zeeman effect works, it's where you've got, in this case, you've got you've got the furnace, and in this furnace, you expose it, to a magnetic field. So if you expose this, to a huge magnetic field, we know that based on the Zeeman effect, if the magnetic field is on, it tends to split, the line source into a continuum. It tends to split it into a continuum, meaning when the B or the magnet, is on, essentially, you've got the holocathode lamp being converted sort of to a continuum, a light source. Okay. And so in that case, really, you'll be detecting, the detector here will be detecting the signal, from the analyte, but also it's going to be detecting the matrix. And remember, the matrix is what is causing, the background. When the B is off, essentially you'll be operating it in a regular fashion, meaning the holocathode lamp is going to be a line source. And so in that case, you're going to be detecting, I think I confused you in this case, sorry. When the B is on, holocathode lamp, is going to be a continuum. And so in that case, you're going to be largely detecting the matrix. When the B is off, because it's a line source, you don't get that splitting effect. And so in that case, you'll be detecting, both the matrix, and you'll be detecting also, the analyte as well, okay? Because this one is a line source. And so if you subtract this, from when the B, in this case, the magnetic field is on, sometimes people call it, symbolize it with this B. When the magnetic field is on, you'll be detecting just the matrix. And when you subtract the two, then, you're actually just gonna get, the analyte signal. So I hope it's fairly clear. Again, when the magnetic field is on, you're converting the hollow cathode lamp into a continuum because of the Zeeman effect, that splitting effect, of a spectral line into a continuum, light source, because of the splitting effect as a result of the magnetic field. And as I said, you'll be detecting in that case, the matrix. And when the B is off, the hollow cathode lamp is a line source, meaning it's going to be detecting, or the detector is going to be detecting the matrices as well as the analyte signal. And so if you subtract the two, you actually get the analyte signal. And essentially that is what I have right here. So that's another way actually of doing background correction. And if you look at the literature, you're going to see that there are lots of instrument manufacturers that actually use this method, of background correction. But we know, that another approach, to correct, for chemical matrices, just to remind you, of course, in the previous slide, we were talking about the background correction as a result, of stuff that are happening within the flame, okay? But if at all there are stuff that are present, in your sample, of course, we refer to that as chemical interferences, which you guys know much well about. For example, when you're analyzing copper in beer, you've got other matrices in beer, such as sugars, and so on. And of course, those types of matrices are going to interfere, with the analyte as well. In fact, other than the sugars, you would expect things like phosphates to be present in beer, things like sulfates, and so on. And we know these types of anions, tend to bind to the cations, that often you're interested in. If at all you're interested, say, in lead, if at all you've got sulfates there, they tend to create lead sulfate. And it's very difficult, to actually break down lead sulfate, just because, you need very, very high temperatures. They tend to be very, very non-volatile, meaning, they are not being atomized, meaning that you are getting, suppression or signal suppression because you are not able to break down the recalcitrant, salts that result from these reaction of the anions plus the cations. And so the way you solve, for some of these chemical matrices that are present in your sample is, for example, you can use the so-called releasing agents. And releasing agents, are typically used, for example, in this case, you're analyzing for, say, calcium in whatever, maybe in a water sample. And we know that water sample probably can contain some sulfates. It can contain some phosphates, if at all it's a wastewater, for example. And so you can add something like the EDTA, which is a chelating reagent. Checking you guys have used it before, ethylene, diamine, tetraacetic acid or tetraacetate, or tetraacetic acid actually. We know that EDTA tends to bind, calcium preferentially, meaning the Kf, the formation constant, is fairly high, meaning that if at all you've got the sulfates and the phosphates there and you add the EDTA, calcium will preferentially react with the EDTA. But we know that the ionization, the ionization temperature, or the ionization energy really, of calcium EDTA is a lot lower, than, say, calcium phosphate, meaning you don't need very high temperatures actually, to cause the atomization, or rather, I should have said the bond energy between the calcium and the EDTA is not as high, and so you don't need very high temperatures. And so because of that, sort of you are releasing, the calcium and making it available, for easy atomization. Now also, you can add other types of cations, say something like lanthanum, that preferentially, react with things like, phosphates. And that way, you're making the calcium available, for atomization, because it would not have been bound, by the phosphate ions, okay? So you can add some of these releasing agents, so that you can mitigate for matrix interferences in your sample. Another approach you can take, is where you use a high temperature flame or even atomizer, such as the ICP. The ICP, the temperatures are very, very high, as you're going to see in a couple of slides to come, like 6,000 degrees Kelvin. And so you'll be able to easily atomize almost anything. But of course, we know ICP is fairly expensive, so sometimes you only have the AAS in the lab, which is going to have a problem, or the flame is going to have a problem atomizing things like the calcium phosphates and so on. So one solution, as I said, is releasing agents. But another thing that you can do, that's a very, very common problem, especially when you're doing AAS, atomic absorption spectroscopy, is this type of interference, referred to as ionization interference. Okay? Remember, with AAS, you want to atomize your sample, all right? But you don't want the temperature to be high enough, to ionize your sample. And the reason is, say if at all you've got a metal such as M, now if you look at, the spectral lines, of M, they're actually fairly different from the spectral lines, of the oxidized form, of the higher oxidation state, of M. So the spectral lines, are different. So if at all you're doing, something like atomic absorption spectroscopy or even atomic emission spectroscopy, ideally you do not want to do ionization of your sample. You just want to atomize your sample. On the other hand, if at all you're doing mass spectroscopy, say the ICP-MS, of course, in that case, you really want to ionize your sample. So you can see the fine line. But when you're doing ICP, atomic emission spectroscopy, you do not want ionization. And so in that case, it becomes an interfering species, because the ions are going to have different spectral lines. So how do you solve this problem? So the way you solve this problem is by spiking your sample with an ionization suppressor, which is a chemical reagent, that is preferentially ionizable relative to your analyte. Okay, I'll give you an example. If at all you're dealing, say, with analysis of, something like calcium, which can be ionized as well. You can spike it, with something like an alkali metal, such as potassium or even cesium, because we know alkali metals, their ionization energies, are a lot higher, or rather a lot lower, than the ionization energy, of the alkali earth metals. And so because of that, the spiked, ionization suppressor really, is gonna undergo ionization faster, than, the analyte of interest. Okay, and because of that, using Richetarius principle, you're gonna see that you've got now an excess of electrons, that are coming from, whatever you spiked, and because of that, the equilibrium, sort of shifts to the left, for the analyte, and so that means you preserve, the analyte, from ionization. I hope it's fairly clear. Again, by spiking it with the ionizer suppressor, something like, an alkali metal, that is very easily ionized, this reaction happens, and so you get an excess of electrons, because you've got a lot of ionization taking place of what you have spiked. And as you well know, with the Richetarius principle, if at all, you get an increase, in concentration, on one side, that forces, the reaction, to go in the direction, where you've got, less of the reactants. Okay. And so ionization suppresses, are typically used, again, if at all you're doing atomic emission spectroscopy or even atomic absorption spectroscopy. For example, in this slide, you're trying to measure strontium, and you're adding potassium. As I said, is an alkali metal. It's fairly easily ionized. As you can see, as you increase the concentration of potassium that you spiked, you can see how steep your calibration is becoming. And as you well know, the slope of a calibration is equivalent to calibration sensitivity, meaning, that your method is becoming a lot more sensitive, because of the spike of potassium, which, as I said, is an ionization suppressor. Of course, we all know that the other option of dealing with chemical matrices, as you guys well know, is to do standardization. Again, remember that. If at all you're dealing with a very high matrix environment, and you guys did it, with analysis of copper in beer, you can do standardization, to correct, for matrix effects. Okay. Now, one other problem that you're gonna face is, especially when you're dealing with AES, atomic emission spectroscopy, is spectral interferences. And I think I remember talking to you guys when we were doing ICP OES, and you are analyzing zinc, you're analyzing copper, you're analyzing lead, in brass. And if you look at, the spectral lines of zinc, you've got multiple spectral lines, say 335, 339, and 520. Copper, has got fairly similar spectral lines, maybe 340 and so on. Lead has got other spectral lines. And so if at all you're dealing with a sample that contains lots of different matrices, or lots of different analytes as well, you tend to have this problem of spectral, interferences. So the way you do that really is to assess what's potentially present, so that when you are selecting, the analytical spectra, the type of wavelengths that you're actually gonna use, you try to stay away, from the spectral lines, from matrices. So again, you have to look at or understand your type of sample, so that when you're making up the method, you can solve, this challenge, spectral interferences. So that brings us to the end of interferences. So remember, we've talked about chemical interferences and the way to solve them, using ionization suppressors, releasing agents, but also doing, something like standardization. But also you've got, the spectral interferences, that comes from the multiplex of different types of signals, that are coming from your sample. And again, the way really to correct for that is just purely by looking at your method, understanding, the type of sample that you're analyzing, and choosing, your spectral lines, analytical spectral lines carefully, so that they are far away, from the matrix spectral lines. So the last few slides, we're going to talk about, other different types of atomizers. I think you've heard me talk now a lot about the flame. We've talked a lot about the furnace, which we talked about. Now we're going to talk about, the ICP or the plasma, type of atomizer, which is sort of, the gold standard, when you're doing atomic emission, spectrometer. The reason why really it's a gold standard, especially ICP and DCP, is because you can see the temperatures are very, very high, meaning it's fairly easy to cause atomization and excitation of your analyte, because after the analytes get excited, you get it to relax, and it emits the spectral lines that you are detecting. So hopefully it's clear, the difference between AAS, and AES. And again, go back and look at the Jablonski diagram that we talked a lot previously. AES is referring to, the relaxation of the excited atom, relaxing back to the ground state and giving you off, those spectral lines, that you are detecting. And then you can see, it's based on this, that you're heating the sample, it's getting dissolvated, but also, it's getting atomized and dissolvated, of course, and then you're getting the excitation, and from the excitation it relaxes back, to the ground state to give you of light, that you're detecting, as your signal. Okay. Now, the most common, again, type of atomizer, for atomic emission spectroscopy is what you refer to as a plasma. And a plasma is an electrically conducting gaseous mixture, with abundance, of cations and electrons. And we're going to talk about, how you actually create a plasma, which you guys already saw, in the lab. The most important thing is that, the plasma temperatures are fairly high, 6,000, even up to 10,000 degrees Kelvin, meaning that they can break down, any type of recalcitrant, or very highly stable type of molecules or salts, that you really want to atomize. So as you can see, atomic emission spectroscopy compared to AES, there are lots of advantages of AES. One of it, of course, is fewer chemical interferences. Why? The temperature of plasma is very, very high, and so it breaks down, literally, any types of chemical interferences that are present. And this explains to you really why you don't really need to care, to do standard addition when you're dealing with plasma, because it breaks down, the matrices, the temperature breaks down, the matrices. So you don't really need to do standard addition when you're dealing with ICP. Now, one other advantage is that you've got a very high dynamic range, and of course all of us understand what a dynamic range is. Another important thing is, and this is very important, you can analyze multiple elements, at the same time. Okay. Remember, AES can only analyze one single element at a time. AES, you can analyze almost everything in the periodic table, at the same time. Now, a couple of disadvantages, of course, AES, as ICP, for example, OES is about 100K, so fairly expensive, compared to a flame AA, which is only around 30K. So again, you can see there's a huge difference, in cost. Now, one other slight challenge, is the fact that you tend to get spectral interferences, with the AES, which I talked to you previously, and you need to look at your method carefully. So there are different types of plasmas, that you can use. Now, the most common is the ICP, and I'm going to discuss, how it's generated. And another fairly common, type is a direct current plasma. And there's an advantage and disadvantage of using either the ICP, or the DCP. But you can also generate really plasmas using microwaves, but again, the temperatures are not too high. And as such, it's not a very, very common, actually, atomizer, for AES. So in fact, it's typically used, as a detector, for gas chromatography. So microwave induced plasmas are not very, very common, for atomic spectroscopy. But ICP is the most common, and to some extent, DCP can be used as well. So let's quickly discuss, how you actually, generate the ICP. So you generate it, you generate the plasma, the inductively coupled plasma, using, a torch, that looks a plasma torch, that looks like that. And in the plasma torch, you've got you've got the sample aerosol, but you also have argon, that is going through, that plasma torch. So essentially, the source of the plasma, is the argon. And so how do you generate, the flame or the plasma? The flame is generated, by passing argon, through a radio frequency coil, okay? So you've got this radio frequency coil, and the radio frequency coil, causes, this argon, to actually break down or get ionized into argon cation, plus, the electrons. And in fact, initially, the way you ignite it is by using the so-called Tesla coil, which is not very different, which is really the radio frequency coil. And a Tesla coil really, is just a high charge, a high voltage wire, or a high voltage, coil wire. And because of that, that causes, the ionization of the argon, into argon cations and argon electrons. Now, we also know that if at all you put a charged species, such as this, in an electric field, such as the radio frequency field, it tends to collide, with each other. They tend to deflect, and collide, with each other. And so, you essentially put in a high, you essentially put in, a high radio frequency field, for the argon and the electrons, and there's a lot of collision, that is actually taking place. And that collision, causes, the heat, to actually get generated. And because of that, you end up, with a plasma. So maybe this figure, is going to explain, all the steps, in a step-by-step version. As I said, you've got a Tesla coil, which is really a high voltage carrying wire, that causes the ionization of the argon to argon cations and so on. And then you put it in a radio frequency environment. And also sometimes you can add a magnetic field, to increase the amount of collisions, that are taking place. And because of those collisions, you create or generate a lot of heat. And so in the end, you've got a plasma, being generated. Now take note of this, you also have an auxiliary, flow of argon, which is actually used, to cool the torch. So you've got, this argon here, that is sort of being used as the one that is generating the plasma. But you also have, the tangential flow, of argon that is used, to cool the torch. And as such, you actually consume, a lot of argon, with the ICP. And argon is not inexpensive. So you can see that the total argon flow, can range from 5 to 20 liters a minute, depending on the type of ICP instrument that you have. And so this becomes very costly, to run. And that's why you saw us in the lab. Actually, we had to pull all the samples together, so that we reduce, the amount of gas, that we are using. So you can run the plasma in two modes, as shown in this figure. You can run it or angle, the plasma either in an axial mode or even in a radial mode, and that means the relative position of the detector to your plasma. Okay, meaning, for example, in the radial mode, your torch looks like that, and then the detector, typically would be at right angles. The detector would be at right angles, to the plasma. Okay. in the axial design, this is where you rotate the torch, such that the detector, you can see it's in line, to the tongue, to the tongue of the plasma. So you can see this one, it's in line, 180 degrees. And then these ones sort of, the tongue here, it's at right angles at 90 degrees, to the detector. Okay. Now, why do you need to do that? You're gonna see with the radio design, which is very commonly used, when you're dealing with a very dirty matrix, such as in metallurgy and so on, you tend to get, fewer spectral interferences, okay? Because you don't get a lot of, this plasma light, hitting the detector, because sort of, it's at right angles, okay? On the other hand, with the axial design, you tend to get more spectral lines, or rather even matrices, because you've got this flame, sort of also heating sort of your detector. But the good thing with doing it this way, you tend to get lower detection limits, higher precision, and so forth. And so it's fairly good, if at all you're doing it, for environmental analytics, or you're doing it for ICP, because the temperatures here also tend to be higher, so ionization is better, if at all you're running the plasma in an axial mode. So again, think about, those two different types of modes and their relative advantages and disadvantages. Again, you can see here, the temperature is lower with the radio, and that's why you're getting fewer spectral lines, which can be a good thing if at all you're dealing with a very dirty, type of matrix. So what are some of the quick features of the ICP OES? And OES stands for optical emission spectroscopy, which is not different from the AES. So sometimes people call it ICP AES or ICP OES. So you can see that it's got fairly good, detection limits. The detection limits really, depend on the type of nebulizer actually that you use. Meaning if at all you use an ultrasonic nebulizer, you tend to get better limits of detection compared to when you use just a regular pneumatic nebulizer like what we used in the lab, the cross flow. It tends to have lower or rather higher limit of detection. The ultrasonic nebulizer just largely means that you've got a crystal, and the crystal, is vibrating. People call it a piezoelectric crystal, that is vibrating. And then you've got droplets, of your solution hitting that crystal. And of course, they break down, into a mist. That's what ultrasonic nebulization means, okay? So you can see nebulizer plays a very significant role. Other features of the ICP, you can see it's fairly expensive, to purchase. But it's also fairly expensive to operate, because of the amount of argon, that you consume in a minute. Now, one huge advantage, like I said, you can actually use it, for multi-element analysis, which is very good. Compared to AAS, of course, ICP OES has got a much wider dynamic range. Of course, compared to AAS, it's got very few potential chemical interferences because the temperatures here, are fairly high. But I would say the biggest advantage possibly is that the ability to do multi-element analysis, which is really impossible when you're dealing with AAS. Now, it's important, to remember that you need the temperature of the ICP, to be very, very stable, because it really, affects, your signal. In fact, you're totally dependent, on the temperature being stable, for you to get good precision. And the basis for that is because of this so-called Boltzmann distribution. And Boltzmann distribution, just describes the relative proportion of atoms, that are present in the ground state relative, to those that are present, in the excited state. Of course, for ICP-OES, we want the majority of the atoms to be in an excited state. That's ICP-OES. Whereas in atomic absorption spectroscopy, we want the majority, of the atoms to be actually present, in the ground state. Okay? And based on Boltzmann distribution, you can actually calculate, the relative proportion of that. And that is also based on proportion, or rather, to the degeneracy. And degeneracy really means, the excited states, that are available, for that atom, or electrons of the atom to transition to. Okay? So meaning, if, for example, you're dealing with sodium, where you've got, say, the 3s electrons, being the outermost, the valence electrons, and then of course you've got the 3p, fairly close, to the 3s, meaning these electrons can transition from the ground state, to an excited state, on the 3p orbital, that is not in the case of sodium in that case. And based on the number of electrons that you can occupy, in the p orbital relative to the s, that is what is referred to as the degeneracy. Okay, all right, and that is what I've shown you here. Say in the ground state, if at all it's an s orbital, it can only occupy really 2 electrons. And then in that case, if at all is excited, then you've got 3 degenerate sort of, orbitals, for the p, and so that's what you've got, the degeneracy there. Now the delta E refers to that energy gap, between the 2 states, the ground state and the excited state. K, is just a constant, a Boltzmann constant, and temperature, really is the temperature of your atomizer. Meaning, if at all you've got a situation like this, where you've got sodium atoms, and you're using a flame, the temperature is not very, very high, and you're exciting the electrons probably, from the 3s to the 3p, and the degeneracy in this case is 2, the degeneracy of that is 1, then the others are constants really, and when you do your calculations, you can see that the n star over the n0 is equals to that. And when you change it to 2610 Kelvin, you see the temperature, or rather the n star over the n0, becomes this. Now, you can see that these numbers are not very different. The 1.67 times 10 to the power minus 4 is very, very close, to 1.74 times 10 to the power minus 4. They don't look very, very significant, because they mean, that largely in either case, you've got about 99.98%, all right, of, the atoms really in the ground state, okay? And so the 10 Kelvin difference, the 10 degrees Kelvin difference, really doesn't affect, the population of the atoms in the ground state, okay? But if you look at atomic emission spectroscopy, between those 2 temperatures, and you take the difference, between these 2 numbers, and you divide it, say, by that number, then you're gonna see that just this 10 degrees Kelvin, causes an increase of 4%, all right, between this and this, between these 2 numbers. Meaning that the 10 degrees Kelvin causes a 4% increase, in the number of atoms, at an excited state. Yeah, meaning that the temperature needs to be very, very stable, when you're dealing with the AES, because it really affects, the population of the atoms, that are present at an excited state. And as such, with AES, you need a very, very stable, type of atomizer. Otherwise, precision, is gonna be poor. So we've already talked about the ICP. The other type of plasma, that you can actually use is a so-called DCP, the direct current plasma. And typically the configuration of the torch, looks like that. You've got 3 sets of electrodes, that looks almost like an inverted Y. You've got the cathode block, you've got, the anode, and 2 sets of anode really, which are made out of carbon, made out of graphite. And then you've got the sample, and the argon, sort of in between. And the way you cause ionization, or the plasma, to actually form, in this case, is by is by short-circuiting the system, where you bring the cathode, into a momentary, connection, with these anodes. So you bring them into connection, all right? And by doing so, you're causing the arcing, so there's a spark. And that spark really, causes, this type of ionization, to actually take place. And, a plasma, is generated because, of course, you're dealing with fairly high voltage, electrodes. And because the spark, is fairly significant, and that causes, the plasma, to actually get generated. Now, compared to the ICP, the temperatures in this case are a bit lower, but you also use less argon. For the DCP, meaning, that that you tend to get fewer spectral lines, for the DCP as well. So very quickly, ICP compared to the DCP, the advantages and the disadvantages. ICP, you use a lot of argon, so that's not very good. You've got more spectral lines, it's good and bad. If at all, because of course of the matrix interferences, which can be a problem. We've got fewer lines with the DCP and so on. Now, DCP can handle more dirty samples as well. ICP, you can't really handle dirty samples at all because of the clogging problems and so on. So the way you operate an ICP OES, because you're dealing with lots of wavelengths in terms of the spectral lines, okay? Because, that's why you're detecting multiple analytes. So how do you detect multiple analytes based on the detector? You can either run the ICP using the so-called sequential mode. And the sequential mode, as I said before, is where you keep changing the angle of the grating, and the angle of the grating, really means that, the spectral lines, different spectral lines, end up in the detector, as you keep, changing, sort of the dispersive element, meaning the grating. But the problem with doing that is that you're sampling only one line at a time, while at the same time you're consuming a lot of sample as you're scanning. People call it scanning. As you're scanning, the instrument, so that you can get to all the different spectral lines. Now, a better approach, is where you make the exit slit fairly wide. And instead of just using one detector, you use a multiplex of detectors called polychromators, which we discussed earlier, things like the CCD. And in that case, the analyte spectral lines, all of them get detected simultaneously. So it saves you time, but also it saves you, the sample as well. And so most instruments, like the one you guys used in the lab, actually used a CCD. So you're not actually scanning, but instead, you're doing a simultaneous detection. So take note, of those two different modes. And lastly, I think it's always important to remember the detection limits of atomic spectrometers. be able to compare relatively, the detection limits, of different types of spectrometers, say the flame AA, the furnace AA, the plasma emission spectrometer, and the plasma mass spectrometer. And you can see, that in general, the plasma mass spec, of course, is a lot more sensitive, very, very low limits of detection. And the flame AA really is not very good, because the limits of detection are not very good. Also look at, things like the advantages, the purchase cost, sample throughput, and so on. Because as you go to the industry, you're going to realize, one of your major role as an analytical chemist really, is to make decisions, on which analytical method, should actually be used. And so these are the metric, figures of merit really, that you need to pay attention to, figures of merit that you need to pay attention to. And lastly, as you well know, if you end up designing an atomic emission spectrometer, you need to be reminded of the different, I guess, ideal conditions or properties that you are looking for, for an emission spectrometer. And almost for any instrument out there, good resolution, wide dynamic range, very sensitive, and so on. And of course, going forward, you're gonna see in future, miniaturization is gonna be a big deal. Ability to miniaturize instruments, to be able to take them to the field, would be a good thing to have. And also the operation cost. You're gonna see one thing that they're trying to do in the industry is to try to reduce, the consumption of argon, because it's the biggest challenge, that we have, with emission spectrometers, particularly the ICP, where they're just too expensive, to operate, because of the amount of argon that is being consumed. And so you're going to see some instruments out there, or some manufacturers out there trying instead, to generate plasma, using something like the air. Okay, it's a new instrument out there. The problem is air doesn't give you a very high temperature plasma, and also causes, of course, the oxidation of your samples, which is not a good thing. Whereas argon, we well know that it's an inert gas, so it causes a very inert environment when you're doing spectroscopy, which is a good thing. So that brings us to the end, really, of spectroscopy in general, especially atomic spectroscopy. In the next chapter, small chapter, really, that we're going to talk about, next time is photometry.